Hello everyone. My name is Lars Haulin. I'm going to present my presentation called Exploring Memory Corruption on Real-Time Operating Systems. Just first, a quick question. Anyone here familiar with real-time operating systems or embedded systems in general? So, a small minority. Memory corruption, a bit more. Security implications from bugs. Yeah. So, who am I? My name is Lars Haulin. I work as a cybersecurity engineer. I have previously been working as an IT security consultant, doing pen testing, and also been working as an embedded systems developer in automotive and medical industries. Engineering physics in the ground on that, but currently I'm a cybersecurity engineer, which means that I do threat modeling, risk assessment, and educate the developers that I cooperate with. I also been playing a lot of CTFs for the last 10 plus years, since before they were called CTFs, they were called war games back then. And I also coach a student CTF team at Uppsala University. So when I take everything that I'm interested in and put it together, risk evaluation, CTFs, embedded systems, electronics, and try to create something that gives a learning experience, I ended up with this project that I'm going to present now. I have created a playground, a Dockerized environment that compiles real-time operating systems with small vulnerable applications. And I wanted to be, the main goal, I wanted to evaluate the exploit mitigation mechanisms that were present in those systems. And I also wanted to be able to emulate a microcontroller without hardware. It is usually best when you have hardware, but if you don't have access to it, it's nice if you can emulate it in a good and easy way. And this is what I prepared in a Docker container. And the side result that I'm going to present here is something that I hope will be useful, interesting, and fun. So overall agenda, there weren't many here who had been having experience with real-time operating systems. So I will mention that a bit and what kind of threats and risks that are present there. Also a bit about the microcontroller memory space that I have looked at. And we're going to do a small demo of the playground I created, some conclusions and future work. I did assume that I didn't have to introduce memory corruption any further, that from the small hands up before, I maybe should mention that it's when you have a programming language where you access memory out of bounds that you're not supposed to. And you can overwrite pointers and make bad stuff happen. And there are protection mechanisms against that. And that is what I'm going to look a bit on. But first out, real-time operating systems. A real-time operating system is a small it's usually small, there are big ones as well. But the main design goal with a real-time operating system is to be quick to respond to events in a guaranteed bounded time. Typically, you have things controlling real-world stuff like engine controllers, pumps, or airplane autopilots, or the quadcopter regulating mechanisms, and those kinds of things. They're usually very tailored to their purpose. They need to be fast, have a low overhead, and execute efficiently. And because of those constraints, they're written in low-level implementation languages such as C, which leads to the question about memory corruption, because those low-level languages usually handles pointers directly and buffers and so on. So there can be memory corruption occurring in these systems. So the threats against these kinds of systems is much the same as normal operating systems. But whereas normal operating systems usually have a focus on confidentiality, that you want to keep the information in the information system secret, when you interact with a real-time operating system, an attacker is often more interested in affecting the function of the system. Same threats, but the prioritization can get a bit different. And most of these threats that we have, they can be caused by memory corruption in programs. So a bug-free program probably doesn't have any memory corruption vulnerabilities. So why don't we just write correct code from the beginning? Isn't that what every programmer thinks about? How do I write correct code? For embedded systems and real-time operating systems, there are a few good standards to avoid this. The motor industry have their standards, and the medical device software industry have their standards. And there are also a lot of tools to go through your code and to see that all bounds are verified. You can also use the newer modern memory-safe languages that are low level, such as Rust, but the industry is a bit slow in this area, so we will see when it comes ahead. But the main conclusion is that writing good, correct code takes time and effort. If we look a bit further into the medical device software standard about software lifecycle processes, the IEC 62303, it's a standard for how to make a risk-based software development. Because if you make a medical device, you need to consider all kinds of impacts it could have on health. And it can be very tedious to follow all this because there are many people involved per line of code written. I think we counted to 9 per line of code in the project I was involved in. And there was in code implementation, direct review, a more formal review, testing, and review of the testing, and then formal sign-off for every line of code. So that's a lot of work. But that is only for the code that you write yourself. What about library code that you import into your program? How do I guess most of us who program have used code that you haven't written yourself. But can you be really sure that it is actually well-behaving and that it does not have any memory corruption vulnerabilities? You can run these scanner tools that are available, but usually when you run such a tool for the first time, you get a lot of warnings. Like, you're missing a typecast here. It's implicit. You need to be explicit. So it can be a lot of effort to do this. So it's a risk-based decision if you want to include libraries and how you go on including it. There is a name in the IEC 62303 for this kind of software. It's called software of unknown provenance. And this is software that either has already been developed, so like normal libraries, or it is some kind of internally based software, maybe from a previous project that hasn't been having a formal development process. So you don't have any guarantees that this code does what it's actually supposed to do. So what you want to do in those kinds of cases, if you have a system that is life critical, like this machine makes sure that a person is staying alive, then you must be really, really sure that you have an acceptable risk level in your software. And the overall goal of this, the highest degree of taking it to the most extreme level is to have code actually running on different processors. You put a small separate processor running the things you want to really control. And then you maybe interface that with a very well-defined communication link to the libraries that you need to use. But not all systems are life critical, so you need to do some kind of reasonable decision to run the code on the same processor. But then you need to rely on other protection mechanisms to make sure that you actually, if there should be a bug, that it's not trivial to exploit. So on normal operating, general purpose operating systems and computers, we have been having these protection mechanisms for a long time. They have also been explored on real-time operating systems. And if you're interested to know more about this, there is a really great talk about this called the RTOS Exploit Mitigation Blues by Jos Wetzels. It has been an inspiration for me when I created my hands-on environment that I wanted to yeah, when I wanted to see those mechanisms hands-on, this talk that I saw made me want to do this. So first, a small mention. I need to mention one thing before we go through to the, and that is such kind of protection. And it's called stack canaries. Anyone heard of stack canaries before? Quite a few. So what it is, for those who haven't heard of it, it's if you have a memory buffer that is on the stack, and you are not sure that you maybe write more to this buffer than you're supposed to, you put a small value here right after the buffer. So if you should write 100 bytes instead of the 20 bytes that the buffer was able to hold, then this value will be overwritten and it will be detected so that you can see that, oh, something wrong has happened. We should abort the execution of this system because something bad has happened. Should ultimately be hard to predict what this value is, because if you know what this value is, then an attacker can fill up the buffer and then write the exact value and then write more data and overwrite other data structures in the systems. But this is one of the protection mechanisms that I've been looking at. I have also been, for my case study, I've been choosing a microcontroller. And there are many, and they have all kinds of strange memory layouts. But I have chosen an ARM Cortex-M processor. It's fairly common in use. It has a 32-bit address space and is well documented. This is, I realize this is a really small picture, but this is from the Cortex-M4 technical reference manual. So the memory, the important thing from this, let's see, I think I can do, no, I can't do laser pointer. Yeah. So the memory is divided into 8 regions. And we have the code memory in Flash and the SRAM, and we have the peripherals. Because when a microcontroller is interacting with this world, it can read electrical signals, write electrical signals, or maybe blink lamps or send radio signals. Then it does this by writing to these memory addresses. So, and this is important because if we get arbitrary memory writes in this processor, then we will be able to write to the peripheral registers and affect things in the physical real world. But the important thing for us to know is like writing to memory can be the same thing as affecting something in the real world. But now on to what I have created. I have created a playground. And what I wanted to be able to was to build, emulate, and debug small real-time operating systems programs. And one of my goals was that it should be easy to set up and use. So I chose to make Docker container to do this for me. And this Docker container automates the download, installation of compiler tool chains, installs an emulator and debugger and source code, and it does everything. So you just start this, build it, and you're ready to go. You can emulate this microcontroller, and you can also debug it using the same container. And I have taken my hobby project and tried to polish it together into something that I dared to show to others, you. And in that I have included 2 separate real-time operating systems. I will mainly be focusing on Sapphire from the Linux Foundation, but there is also, I also included one example application for free RTOS, because I will come to later why I did that. So the usage for this one, it's just git clone, change directory, run the build and extract script, but you can't do this now because it takes 25 minutes and I don't have that much time. And then you just do docker compose run with this application. So this simple stack buff for buffer overflow is a demo app. Oh, sorry, not that. This is what it looks like. So it's just a small vulnerable function with a small buffer. and it prints out the prompts, and then it reads a line and copies to this buffer. And if you write if this buffer is only designed to contain 32 characters, if you write more, then we will overwrite control structures in this program, and we will probably make it crash. But I will now do a live demo of this. So here I am. Is this too small? I can probably change the font size a bit. So here we are in the. I have cloned and I've cloned and built it. So it won't take 25 minutes. So and we just do we run this stack buffer overflow container, and the -rm is because I don't want to keep it after I've done, so it will just remove it. So we run this. Takes a while, but then the emulator starts. So we can do something, and it will copy things to the buffer. But if we write more than 32 characters, do you have any guess what will happen? Well, yes, it would have been segfault if we had been on a higher level operating system. But this is a low level operating, so we get a memory protection unit fault, which is a bit more closer to the metal. But we get this instruction access violation that we're trying to execute on this address 41414140. And the hexadecimal character for the big A is 41. And the reason that we get 40 is because on ARM, the lowest bit in an address is used to specify if it should be a 16-bit or a 32-bit instruction. And they are always 16-bit aligned. So that's why it's not 41 in the end. So right now, you can see that it has hanged. But what we can do is this is QEMU. So we can enter the monitor. We're doing Control-A-C. And we can quit. And then we get back to bash instead. So back to, so this was the simple stack buffer overflow. But what can we do to add protections here? We can use this exact same code, but we add this line to the build config to use stack canaries instead. And I have prepared that as well. So should be canary. Yes, tab completion takes a bit of time. So if we run this, it looks, this function is the same. Should be at least. But now if we try to do this, what do you think will happen? Will the same thing happen? No. We can try. We can test out. This is hands-on. We get stack check fail. So even before we try to execute memory at this address that we overwrote, the program recognizes that something as bad has happened to the memory layout. So the execution is aborted. And that is, so that is how the protection for that works. I will also make a third demo, how does debugging work on this? So I have prepared now 2 terminals. So what we do then is we run this. We can write the same with the canary. But now we also need, when we want to do debugging, we should specify that we want to be able to communicate with the network ports on this. So we add the service ports and then start this. No? What did I do wrong? Oh, right, thank you. Yeah. So now, when we want to enable debugging, we should go in RTOS presentation, RTOS playground, Sapphire. Sapphire is the operating system we're using here, so the one from the Linux Foundation. So what we do now is we do almost the same. We do docker compose, run rm, and the stack buff. But now we run this with a special command. We run it with the debug. But before we run this, we want to tell the original emulated program that we want to listen to GDB. So we open the monitor for QEMU with the control AC, and we do GDB server. Now we're listening for a GDB connection to this device, and we start the debug script here. And this will start a GDB, and it will run it and connect it. So we connect, and we can see that when we connected, we were in CPU idle. Great. So we can go back to the normal. So we can now that this program is running, but we also have the debugger. So what we can do is to let's say we break. And we disassemble this vulnerable function. It's called vuln. I don't know how many here read ARM assembler fluently. Yeah, a few. So these are the microcontroller instructions that are running here. So what we want, we can look at the function calls. It runs it says print, and then it gets a line, and then it does a string copy. And then it is some kind of conditional jump, and if here it compares two registers, and if they are not equal, then it will call this stack check handler. So we would like to break just before this stack check. So that would be here, before they are compared. So we do a break at this point. Continue, and if we now write something short, we don't want to crash, we can say we get a break. And if we then look at the R2 and R3, you can see that these values are the same. So we continue. So we make something a bit longer. So what happened now? We make a breakpoint, we look at the registers. We can now see that one of these values have been filled with 41s, so they are not the same, and they will not be. But something that we can notice here that I don't know if I have done a mistake in my compilation setup, but can you see something strange about these two values here from the first run and the second run? I mentioned before that the canary values should be hard to predict, but in this case, they are the same both times. So this value here is, it starts with a 2, which means it's a RAM address. So if we look at what this actually is this is the address of the stack check guard. It's not the value of the stack check guard, but the actual address of it. So that is a bit sketchy, and I'm not sure if I have made something wrong or if someone at the operating system has made something wrong, but I will look into that, because if it is not me, then it's bad. So what I wanted to, but even if we look at the value of this canary, we can see that it is quite small. So I was looking, it's mostly zeros and then a small value. So if you run this a few times, I did this about 1,000 times. I noticed that I made another small program that just printed out this value, and I saw that they are always low. And the value of this stack canary, it's set to the number of clock cycles it takes to boot up. That is not the same all the time, but it's not very different either. So I made is cumulative probability distribution also something that is not heard of? Yeah, well, this is like, is this how common, how the values are distributed. And if it's steep, then it means that there are many. So there are quite a lot that only take like C00 clock cycles to start up. This is about 3,000, and this is about 6,000 if you look at it in decimal. So there are only about 3,000 values, but with a high skew against somewhere between 3,000 and 3,500. So this is not a lot. I tried to compute the how much information content this actually have, and it's about 6 to 10 bits of entropy, which means you need to try about 500 times before you can guess this value. So this is in my setup. This microcontroller that I used did not have a cryptographically secure random number generator. It had to use something that was different all the time. So it used the clock cycles. This can be improved on, but still not really optimal. So as a summary, this playground is available on GitHub, and any pull request issues, anything is very welcome. It's GitHub, RTOS Playground, RTOS Playground. And for the future, I plan to add some more examples. There are some printf examples as well that I didn't show now. But I also plan to do some heap threads. The reason I included FreeRTOS is because it has 4 different types of heap implementation regarding on what kind of performance or you were looking for, if you're looking for speed or memory efficiency. Also, naturally, documentation tutorials, more RTOSs, and perhaps the possibility to run this on real hardware targets. So that's me. That's all I had. And thank you for listening to this.